Thank you very much for having me here virtually at this workshop today. Today I'm going to talk about robust driving policies, in particular two projects, which are a collaboration with my postdoc Eshet and my students Aditya, Kashyap, and Asim. Imitation learning has emerged as a powerful paradigm and a simple paradigm for training self-driving agents. In contrast to modular pipelines, where a lot of decisions must be hard-coded, which is difficult, imitation learning follows a data-driven approach, where given a set of demonstrations from an expert, the goal is to train a policy that mimics the decisions, that mimics the actions of that expert. Here we see an example. We see some expert trajectory on the top left that gives rise to a data set of observations and action. And then there is a supervised learning, a machine learning model that's trained in a supervised fashion to map these images, in this case, to the actions in the form of a regression problem. And then at test time, we can simply execute that policy. One state-of-the-art model for imitation learning that works well in realistic simulators, such as CARLA, is CILRS, which has been published at ICCV last year. CILRS uses a convolutional network to map the image to the vehicle controls. But in addition to that, it also receives the navigational command, because it's important for an imitation learner to know where to navigate to at the next intersections, where multiple directions are actually equally feasible. That's why it's called conditional imitation learning. In addition, a speed signal is fed into the driving policy and is also predicted again in order to regularize the driving policy to not get trapped in some behaviors that are called causal confusions. The advantage of such models are they are end-to-end trainable and the annotations are cheap to acquire, as we just need to put a camera in a car and drive around and record the signals of the steering wheel and the gas pedal as we are driving. However, existing models are limited in their generalization. They suffer from high sample complexity and covariate shift with respect to new distributions, and also they are not very interpretable. Let's have a look at some results of some of the imitation learning models that we have trained in our lab. Here you can see an example of the CARLA simulator that we use a lot in our lab, and that even in that simulation, self-driving is difficult because you have to yield to traffic lights and to pedestrians. And there's many things that can actually go wrong. Here we see some failure cases, like not yielding to traffic lights, or stopping in front of a reflection by misidentifying the reflection as a pedestrian, or crashing into another vehicle, or driving off-road, or even hitting other people, for luckily only virtually here. The question we ask in the first project that I want to present is, how can we learn to drive under vast diversity of all visual planning and control scenarios in the real world, or in a realistic simulator that tries to mimic the real world? Let's look at some situations in CARLA. So here we have one of the conditions, which is sunny and light traffic. Now we switch to sunny and heavy traffic. Now we switch to rain and heavy traffic. Now we switch to sunset and heavy traffic. So as you can see, all these scenarios are quite diverse. There's diversity in the situations that need to be tackled, but also in the weather conditions. And an ideal model should generalize to all of them. In this project, we took inspiration from the World Models project from Schmidhuber et al., published at NeurIPS 2018. The idea of world models is to learn a generative model of game environments using a variational autoencoder. They used this OpenAI Gym car racing simulation and a battlefield simulator and trained a latent space representation using a VIE in an unsupervised fashion. Now, given this latent space representation, each input image can be mapped to such a latent code, which allows to learn dynamics model in the latent space, in this case using CMAS. However, we found that this model alone is not sufficient. The reason for this is that this VIE abstracts the visual image too much. It still works for these relatively simple scenarios that I've shown here, but if you apply them to the real world, to CARLA, we found them to not work well. Because if you abstract this image here into a latent code, a purely reconstruction loss-based approach does not know what is actually important in that image. And as the visual complexity increases, it becomes harder and harder for the autoencoder to actually abstract that image. And relevant information is soon starting to miss, such as the small number of pixels in the image that are, for instance, responsible for the traffic light state. In our work, we combine these ideas with imitation learning to get a more powerful model that also works in situations that are as complex as the CARLA simulations that I've shown you before. And this is our model. It's called learning situational driving because we try to capture multiple situations, as I've shown you before, not having just one single imitation learner, but to have a set of imitation learners. This is illustrated here. Given a set of environment and demonstrations, we learn a number of imitation experts that we then use jointly to derive an action. And we learn this mixture of expert policies jointly via imitation learning. Next, we learn a general purpose context embedding using a beta VIE. This is similar to the world models approach. This gives us some context of the overall structure of the scene. And finally, we combine these two into an action that is further refined using task-driven policy refinement. Note that training a model using imitation learning does not optimize for the actual desired target quantity, which is, for instance, in CARLA, the success rate, how often you reach the goal actually. But rather, you optimize for the correct action. Therefore, we use a task-driven refinement where we optimize the final layers of these networks using an actual reward, such as success or infraction rate. And we do this using an evolutionary algorithm. So here is an overview, a formal overview of our model. Pi denotes the driving policy and theta denotes the set of all parameters, where these parameters comprise little theta and also phi. The driving policy takes as an input the observation and the conditional command and produces a distribution over actions, A. In this case, we have a two-dimensional action space, which is move forward or accelerate and stop, and left and right. And we have 4 conditional commands, left, right, straight, and follow, which are provided to us by the CARLA environment. And the observation is an image. And because we don't use a sequence, we also input the velocity as in CILRS as an observation. This model is composed of 2 parts here. So the first part is a mixture of k experts, where we have a weight that's also parameterized by a neural network, and the actual expert driving policy pi. And then we have this context embedding Q that takes as input the image, and the velocity and the conditional command that are linearly combined using this parameter psi. Each expert on its own is modeled using a Gaussian distribution where the mean and the variance are represented using neural networks. Now, training works as follows. In the first step, we learn the mixture of experts, and we do this by minimizing an imitation loss, in this case, a mixture of experts imitation loss, as well as a loss on the velocity, which regularizes, as in CILRS, and a reconstruction loss, which is a further regularizer. In the second step, we learn a context embedding. We learn this context embedding using a beta VAE similar to the world models paper. You can see the formulation of the beta VAE. You have the encoder here. You have the KL divergence between the encoder and the normal distribution. And you have the reconstruction loss here on the right. So this is a purely image-based reconstruction loss. And then in the third step, we perform task-driven optimization using an evolutionary algorithm that optimizes the expectation of the reward with respect to the driving policy of the entire model. And we do this with respect to these parameters here and the last parameters in the last layers in this mixture of experts model. So let's have a look at some of the experiments that we conducted. We used the CARLA benchmark, which is composed of a training town and a test town. And there's a random start and end location and need to traverse successfully from the random start to the random end location. In the standard benchmark, there are 4 known weathers and 2 unseen weathers at test time. And the metric is simply the percentage of successfully completed episodes. In other words, the success rate. However, in this standard original CARLA benchmark, collision does not necessarily terminate an episode. Therefore, we also considered the NoCrash benchmark, which is more challenging. Now, collisions actually terminate episodes, so count as non-succeeded episodes. And the difficulty varies with the number of dynamic agents in the scene, which goes up to 220 agents per city, which is quite dense and much denser as in the original benchmark. And we also propose an additional benchmark, which is the AnyWeather benchmark. Instead of evaluating on 4 known and 2 unknown weathers, we evaluate on all 10 unseen weathers that are provided in the CARLA simulator, which is much harder and quantifies generalization performance. As you can see, the diversity between the environmental weather situations is large. We first conducted a study on the importance of the mixture model. What you can see here is in columns, the training data and mixture components. So this is, we trained in this case here, for instance, on the navigation task, on the static navigation task. So static means no dynamic obstacles and dynamic means dynamic obstacles. Using 1 mixture component, here in this case on a dynamic task with 1 mixture component, and here on a dynamic task with 3 mixture components. What we can observe is that the static model solves static scenes well, but cannot handle dynamic objects. So if you train a static model, it will work very well on the static scenes, but will just drop dramatically in performance on the dynamic navigation task. Furthermore, the dynamic model handles dynamic scenes better, but surprisingly degrades performance on the static scenes. So this comes with a loss in accuracy at the static scenes. However, the dynamic mixture model that comprises multiple experts, each of which can specialize to one particular scenario or environment, generalizes well to all scenarios, even without any on-policy data. So in this case, we didn't use our CMAES policy refinement strategy, but we just used the mixture of expert component. Next, we investigated the importance of the mixture model and the task-based refinement. Here are some results of the full model on the CARLA benchmark. What you can see here is a monolithic approach with 1 mixture component, then the mixture of experts with 3, 5, or 8 mixture components using a shared backbone or using a separate backbone. And furthermore, a mixture of expert with a separate backbone plus the reward-based or task-based refinement strategy. As you can see, performance improves up to 3 or 4 or 5 mixture components from 75 to 89 or 94. Furthermore, a separate backbone increases diversity. If you have a shared backbone, diversity decreases. So having more diversity in your experts is actually better. So at a slight increase of runtime, you can get better generalization performance compared to the shared backbone. And what we also found is that the task-based refinement strategy improves performance further. So this is including the context model and including reward-based optimization. And we also found that there is actually different driving modes emerging. So here we look at the distribution of the different experts at one particular input image. And we can see that this is the acceleration distribution. And we can see that the acceleration distribution of the 3 different experts varies significantly during testing. So it seems like each expert has specialized to one particular driving behavior. Now we show some results on the CARLA benchmark. So here we have the driving task on the left, straight, one-turn navigation or navigation with dynamic obstacles. And we see that the baseline CILRS degrades with respect to the difficulty of the scenarios. Furthermore, using reward-based optimization, this is a method that uses reinforcement learning of an imitation learner or a model that's initialized with an imitation learner is not sufficient alone to generalize well to complex environments. LSD, in contrast, enables better driving behavior across all driving tasks. And you can also see large improvements in the presence of dynamic obstacles. What you can see here is our approach. It's called Learning Situational Driving, short LSD, and LSD plus R denotes the version with the reward-based optimization. Here we see some results on the CARLA NoCrash benchmark, which is significantly more difficult, as you can see, by the degraded performance on all models. And the reason for this is the higher density of the objects, of the dynamic agents, and the collisions that terminate the sequences. What we also observe is that even the expert provided by CARLA often fails in these environments due to clogging. As scenes become clogged, there's just no way to reach the goal in time with valid driving behavior. However, what we can also see is that we get quite close to this expert performance, and our approach enables much better driving behavior across all these different tasks. Here's finally some results on the AnyWeather benchmark, which is the most challenging amongst these 3. The AnyWeather benchmark tests generalization to challenging unseen weathers by including all 10 weather situations, and we compare our method to CILRS. What we can observe is that all methods can fail even on simple straight driving tasks. These are average numbers, but if you split them over the environment situations, then you will see that even for some simple straight driving tasks, if the weather situation is difficult enough, the methods can fail because we just become too cautious or we get off-road. And some challenging weather scenarios lead to 0 success rate even for all methods. This means that this benchmark remains a challenging benchmark for further evaluation of driving agents. And more research is required to address these challenges. Let's look at some qualitative results. Here we see CILRS. Where we observe a collision with a pedestrian and a lane infraction, getting off lane. We tried to produce exactly the same scenarios for our model. You can see it didn't stop correctly for the traffic light, but it stopped correctly for the dynamic objects. It's actually quite difficult to test in the CARLA simulator for exactly the same environment, because as soon as you start unrolling, the situation develops differently. But we tried our best to find situations like that. As you could see, sometimes pedestrians just even die without doing anything about it. They just walk under your car and you cannot do anything about it. So this is a deficiency of the simulator. It's impossible to reach full success rate on this task. So here we have a comparison between LSD and LSD plus the reward-based refinement. You can see that the reward-based refinement helps overcoming some of these very challenging scenarios where the agent times out due to a reflection. In the second project, we were wondering, well, how useful is data aggregation for self-driving? In the first project, we were using a form of reinforcement learning to fine-tune the agent. But if we do imitation learning, what we can also do is we can use data aggregation. So what is that? Let's look at the imitation learning pipeline again. So this is the slide from before where we have the expert trajectories that give rise to a data set. And then we have the imitation learner that's trained in a supervised fashion for the policy that we want. The formal definition of imitation learning is as follows. Here we have the general formal definition where we want to find the parameters over the expectation of the policies with respect to the loss function and the output. The loss function is with respect to the expert behavior for that particular state that is sampled from this distribution, and the output of our trained policy. So in this case, importantly, the state distribution P depends on the rollout determined by the current policy, pi theta here. So this S is sampled from a distribution that depends on the current policy. So there's a interleaved interplay between the two. In behavior cloning, that is what we typically do for imitation learning because this is infeasible. What we do is we first collect a static data set. So this is now not depending on the current policy anymore. And we sample state, as our observations and action pairs from the static data set and train a loss function that tries to minimize the difference between the true action and the action predicted by our model for that particular state. In this case, the state distribution P star is provided by the expert and collected such that it can be trained offline. Therefore, this reduces to a supervised learning problem. It has a much simpler diagram. Now, the problem with behavior cloning is that behavior cloning makes this IID assumption. The next state is sampled from states observed during expert demonstration. Thus, the next state is sampled independently from the action predicted by the current policy. What does it mean? Well, what happens if the policy makes a mistake and the next state is actually not the next state that would have happened if I would have followed the expert? Can never assume the policy to be exactly the same as the expert. Well, then we enter a new state that has not been observed before. That's not part of the data set. These new states are not sampled from the same expert distribution anymore, and this can lead to unrecoverable catastrophic failure. Right? You get a little drift, and then you drift off more and more. And this is also there's also evidence for this kind of results by early experiments from Held and Hein in psychology, or physiology, where maybe you've seen this before. They have put a cat in such a basket here, and this basket was moved by another cat, and that was a newborn cat here. So what they wanted to test with this is, can this cat learn the behavior of walking just by watching? And it turns out that it can't. So you really need the interaction with the environment. You really need to observe your own errors to improve your policy and to improve your behavior. Therefore, Dagger has been established as an efficient way of generating more training data in order to avoid such cases. So this is an on-policy method now. It's not off-policy as standard behavior cloning, because once we have trained a policy on an offline data set, we go to the environment, do rollouts, and see where the policy performs well and where it doesn't perform well. And then we take all the rollouts as the new states, aggregate the data set, and query the expert on these new states again, and do rollouts again, and so on. So until we cover the entire state distribution, or at least the relevant state distribution for the task. In other words, data aggregation, short Dagger, iteratively builds a set of inputs that the final policy is likely to encounter based on previous experience. And it iteratively queries the expert for the aggregate data set. However, what we found is that Dagger, in its standard form, as successful as it is in classical robotics tasks like manipulation, it can easily overfit to the main mode of demonstrations, in particular if the data set distribution is very unbiased. And that's often the case in self-driving. Furthermore, there's a high training variance that we have observed, which means that if we randomly initialize the model for training, so we randomly initialize the parameters of our model for training, just by setting a random seed, or we choose the order of the data in which we see the data set differently, the variance in success rate at test time can be very high. That's what we call high training variance. So the problem with the uneven distribution is illustrated here. What you can see here is the distribution over brake, steering left, go straight, and steering right that we pass on in forms of a data set to the imitation learner. Now if we apply Dagger over the iterations of Dagger to this data set, to increase the data set, the unequalness in the distribution, the biasedness of the distribution stays. There's always less braking scenarios observed in the data set. And that means that these scenarios will fail more frequently. So the key ideas that we present in this paper that we also present at CVPR this year is that instead of sampling all the states through Dagger, we sample critical states more often from the online policy, based on the utility these critical states provide to the learned policy in terms of the driving behavior. And second, because this alone is not enough, it actually even leads to more overfitting, we incorporate a replay buffer which smoothens out the results by progressively focusing on the higher uncertainty regions of the policy state distribution. Having both components here in green together was critical for our approach to work. So now, compared to the previous diagram here, we have a data set, a policy trained on a data set that's rolled out, and then we get on-policy data, but now we sample that on-policy data intelligently for critical states that we feed to a replay buffer that automatically maintains a useful distribution of data samples in order to maximize the benefit, the training benefit of the policy. For the sampling of the critical states, we use 3 different strategies and compared it in our paper. A task-based strategy where we, for instance, sample uniformly from the control commands, the navigational commands. A policy-based strategy where we use test time dropout to estimate the uncertainty in our model. And an expert-based strategy where we use the highest loss or deviation in brake signal with respect to the expert actions. More details on the selection of these strategies can be found in the paper that is listed here below. Now, using this critical states in the replay buffer, we can see that starting from this bias distribution during imitation learning, over the iterations, over time, here you can see iteration 1, iteration 2, iteration 3, we obtain more equal distribution. Without explicitly specifying that we want more equal distributions, we obtain more equal distributions, which demonstrates that the model learns more equally to respect the different environments or different tasks. So let's look at some experiments. For these experiments, we focused on the most challenging scenario from before, the CARLA NoCrash benchmark with all 10 weathers in the dense setting. So we just focus on this dense setting. That's why the numbers here are lower than the numbers that you've seen previously. And we compare to various baselines with or without data augmentation. Dagger is not the only way you can do data augmentation. Dagger is an automatic way of obtaining more samples, but you can do also local data augmentation, which is, for instance, also used in CILRS. For instance, by simply disturbing the trajectory of the expert and then letting the expert navigate back onto the road. And this is what we found. So here we can see when we evaluate on the training conditions what happens. What you can see here are all the baselines. There's the expert, this is the upper bound that we can obtain. There's the CILRS baseline here, this is this line, and there's the CILRS plus baseline, this is this line here, which are the baselines. CILRS plus, just to repeat, is the CILRS baseline using these triangular perturbations for data augmentation. So what we want is effectively that all these curves improve upon the baseline, and they do, Dagger does. But note that Dagger improves only until a certain iteration and then even degrades again. In contrast, the proposed technique, DRAB here, increases further. This is this brown line from this starting point here. And when using the additional data augmentation or even an ensemble can yield even stronger results that are rivaling expert performance. We note that data augmentation increases the performance of all methods and that Dagger overfits quickly, which is in contrast to some of the observations that have been made in the literature for classical robotics tasks. And it's not better than regular data augmentation. As you can see, this cyan line here moves only up to the point roughly where the regular data augmentation performance is obtained. In contrast, our model consistently improves upon the baselines in all conditions. And this is true also for the other conditions. Here we see the new weather condition and the new town condition. What we also observed, so these are similar numbers just in terms of a table, is that the ensemble E improves performance further in most scenarios compared to the baseline without ensemble. And what we observed is that, as in the previous paper, the expert provided by CARLA often fails in dense environments due to clocking. So this is really the upper bound that we can achieve in this simulation environment. We also looked at the infractions. Here in red, you can see CILRS, and then in green, our approach without and with ensemble setting, as well as the expert. What you can see is that we reduce collisions significantly with respect to this red baseline here, in particular for dynamic obstacles. However, we obtain more timeouts, which is clear because in this particular simulation setting, there is just some scenarios that cannot be solved due to clocked scenes or red lights, or where the vehicle has to stop and just doesn't arrive in time at the destination. That's why the timeout scenarios have increased. We also looked at the training variance that we were just discussing before. What we did here is we used 5 random seeds, which we recommend to report for all papers published in this setting on CARLA. And we compare then the variance of the successfully completed episodes at test time. You can see the performance of CILRS, the performance of Dagger, or the variance of Dagger, and the variance of our approach. As you can see, in our approach, the variance continuously decreases. But for Dagger or for CILRS, the variance is quite a bit larger. This indicates that the sampling the data set based on these critical states might be crucial for variance reduction. We also looked at GradCam attention maps and found that our approach focuses more often on relevant aspects of the scene compared to the CILRS baseline. Here we show some qualitative results. You can see CILRS on the left and DARB, our approach with replay buffer, on the right, both approaches including triangular perturbations for data augmentation. Again, we tried to find scenes that are similar to each other so that we compare the behavior at the same location in the environment using the same objects. Okay, so let me briefly sum up. In this talk, I've demonstrated that a single imitation learner cannot accurately capture the complexities of real-world driving, and that a mixture of experts instead can significantly improve generalization performance. I've also shown that task-driven optimization is difficult but important. Data augmentation is also important but can easily overfit in self-driving. Sampling critical states in a replay buffer improves aggregation performance. I've also shown that training variances can be significantly reduced using the same strategy. However, generalization to all CARLA weathers, in particular the difficult ones, remains unsolved. and better experts and improvements in the CARLA simulation are needed. However, I also want to highlight, I'm very excited about this, that these improvements are on their way. There is currently the CARLA version 0.99, which we are testing at the moment. That's all from my side. I want to thank you for your attention. I want to point you also to our blog page where you can find more information about our research. Thanks.